The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone and welcome to our webinar, which is titled An Introduction to LimitState SLAB. This is the 11th in our 2015 series of webinars that discusses LimitState products with a particular focus on their features and practical application. My name's Tom Pritchard. I'll be introducing you to our first speaker, who is Professor Matthew Gilbert, in just a moment, and then following his presentation I'll take you through a number of example problems using the software. We hope that the session will provide you with an understanding of the novel technique by which LimitState SLAB has become the first software to systematically automate the Yieldline methodology, as well as demonstrating the wide range of SLAB analysis problems that you can actually solve with it. The presentation part of the webinar is due to last about 50 minutes, and then there'll be 5 or 10 minutes at the end for questions. These can be posted at any time during the webinar using the question panel that should be present in the interface that you have on your screens. While we do try to answer as many of your questions as we can in the time available, obviously this isn't always possible, so if you would like, you can also email us at the end via info@limitState.com or by telephoning during UK office hours, and we'll be happy to speak to you in detail afterwards. We'll also try and answer any questions that are posted personally after the webinar has ended. So without further delay, I'd like to welcome you to our first speaker today, who is Professor Matthew Gilbert, who will be speaking about the methodology of automating the Yieldline analysis method. So I'll now pass you over to him.
Thanks very much, Tom, and thanks to everyone for joining us this morning. Okay, if a picture is worth 1,000 words, then hopefully the first image will illustrate to you the power of LimitState SLAB. The images on the left-hand side are yield line patterns, which you might derive by hand. The images on the right are yield line patterns that have been identified by LimitState SLAB. Clearly, the standard Yieldline method is powerful, but by hand it's very, very difficult to find the critical mechanism when the geometry, loading, and material properties are complex, and that's where LimitState SLAB comes into its own. And the next slide shows you what those yield line patterns mean in terms of failure mechanism. So simple mechanisms as you expect on the left-hand side, and more complex mechanisms which would be very difficult to identify by hand on the right-hand side. So what I'm going to do today is to briefly introduce you to LimitState, the company, and then explain to you how the software identifies a yield line pattern for general problems. First of all, then a few words about LimitState. It's actually a University of Sheffield spin-out company. It's commercializing academic research with a view to providing engineers with powerful ultimate limit state analysis and design software. And the key thing that we do is we take advantage of state-of-the-art optimization algorithms to rapidly and robustly provide an indication of the ultimate limit state behavior. And as a standalone company, we're able to ensure the applications are easy to use and are fully supported. At the moment, we have 3 main products, all ultimate limit state analysis products. So LimitState Ring for masonry arch bridges, LimitState Geo for geotechnical analysis problems, and of course LimitState SLAB for concrete slab analysis software problems, should I say. And each of these tools is now widely used. In the UK, most major consultants are using one or more of the products, and the products are also used in more than 30 countries worldwide. And this next slide just gives you an indication of the companies that are using the software. So big companies like AECOM, Arup, Atkins, Balfour Beatty that you may have heard of. Okay, so what is our motivation? If you step back and look at the engineering analysis field as a whole, what you can observe is that the finite element method has really made linear elastic analysis convenient and mainstream. So it doesn't matter what the geometry is, we can rapidly and effectively get do a linear elastic analysis of a complex component. The same can't be said if we're looking at ultimate limit state analysis. So rigid plastic analysis tools, which were on a sort of even par with linear elastic analysis in the middle of the last century, haven't really kept up at all. And we end up often having to rely on hand-type methods in order to do an ultimate or collapse analysis. So I mentioned rigid plastic analysis. What do I mean by that? Well, it's a rapid means of estimating the maximum load that can be carried by a body or structure. So what we typically assume is that we have no deformation prior to collapse and then perfect plastic response at collapse. And the key benefits compared with elastic methods, if you're thinking of ultimate analysis, are firstly that you end up with more economic solutions when you're using them in a design context, and you can often identify hidden reserves of strength when you're using rigid plastic methods in an assessment context. So just again, looking at this sort of big picture view, what we've got as engineers are two types of tools which we can apply when we are interested in collapse analysis. So traditional hand-type methods, possibly embedded in a spreadsheet or simple program at one extreme, and the other extreme we have nonlinear finite elements, discrete elements, and a whole wealth of advanced tools which are complex and require significant expertise and often runtime to get solutions. The key thing is that we've identified there's a huge gap between these two types of tools, and what we're interested in doing is filling that gap with mainstream tools that use numerical rigid plastic analysis. And those type of tools can be applied to geotechnical problems, as in the slide that you can see here. Could also be applied for masonry problems, so we're analysing masonry arch bridges in the current slide. Or obviously of interest today, we could apply the same techniques to concrete slabs. So in the context of concrete slabs then, the Yieldline method is a well-known technique. It's actually the term at least was coined almost a century ago by Ingerslev. I think it was in 1922, a paper appeared in the Structural Engineer, and Johansen, a Danish scientist and engineer, picked that up and developed a very comprehensive theory which led to the development of what we now know as the Yieldline method. And that was later shown to be an upper bound plastic analysis method within the context of the plastic theorems which were developed in the middle of the last century. So what does that actually mean in practice? Well, it means that we can analyze the capacity or provide a prediction of the strength of a slab relatively easily using hand calculations, at least if the geometry is simple. So what we typically do is we'd guess a mechanism, we then deform that mechanism, and then we would typically equate internal work done by the yield lines to external work done by the loads. Advantages of the method is that it's a direct and relatively rapid means of estimating the collapse load, and obviously in terms of economics, you get to economical designs and realistic assessments of the capacity of existing slabs, at least compared with elastic methods. The negative side, if you don't choose the right mechanism, so if you don't choose to guess the correct mechanism, you'll end up over predicting the strength of your slab. And another con is that it only considers flexural failure, so it doesn't consider, for example, shear failure. And also, clearly, because we're looking at the ultimate limit state, we're not concerned with deflections at serviceability limit state either. Okay, so certainly in the UK, about 20 years ago, there was renewed interest in the Yieldline method. Middleton and co-workers at the University of Cambridge demonstrated that many concrete bridges that had been designed using elastic methods were in fact able to carry the increasing vehicle loads that were required of them. And we can see here a bar chart where we've got the elastic capacity in red and the plastic capacity or Yieldline capacity in green. And what you can see is that many of the bridges had significantly more capacity when analysed using plastic methods compared with the elastic assessed capacity. However, at the time, Middleton used a lookup table, effectively, of possible failure mechanisms, and implicitly, the assumption is that the critical failure mechanism for these bridges is one of these 27 mechanisms shown on the right. Now, it's perfectly possible that actually, in the case of, for example, bridge 14, mechanism 28 was actually more critical. Mechanism 28 clearly didn't exist in the program, and hence the assessed capacity would be unsafe. So there's always a nagging doubt when you use this kind of technique that you've missed the correct failure mechanism. Around the same time, there was research undertaken in the UK around an ambitious project. There's a large airship hangar was used to construct full-scale steel and concrete buildings, and the concrete building had floors that were designed using a variety of different methods. And when the Yieldline method was used to design the floor in one area, it was found that actually the amount of reinforcement was lower than using any other design technique, and also crucially, the layout of reinforcement was pretty simple. So there was 22 bar marks per floor. So it was simple and economical. So their conclusion, the people involved in the design of that floor commented that Yieldline design is so easy once you know what you're doing. And the big problem is that they couldn't persuade enough engineers, certainly in the UK, that they did know what they were doing to actually fully exploit the economic advantages of the method. So what I'm going to do is just jump in and use the software briefly before explaining how it actually works, and then my colleague Tom will talk you through using the software in a bit more detail. So I've now got the software on screen. What I'm going to do is actually I'm going to define a slab from scratch. I'm going to have an empty project. There are a couple of options. If you've got a simple rectangular slab, then the wizard would allow you to define that in a very easy way. But I'm going to actually use the empty slab project. So I can enter some details of the project if I want, and I can give some information about the dimensions of the slabs to help me draw that more effectively. But for now, I'm just going to click finish, and what I end up with is just a grid. And what I can do is I can use the drawing tools on the left-hand side to simply draw a slab. I'm just going to do this freehand. There are other ways of doing this that Tom will talk you through. So, for example, reading in a geometry from a DXF file is a popular option. I'm just going to freehand draw a slab, just clicking to the grid points. What I can do now is just hide the grid, and what I now need to do is define some supports. So what I'm going to do is actually define some of the supports to be simple. So I've got 1, 2, 3, 4 simple supports, and I've got 1, 2, 3 free edges. For now, I'm going to just apply a kind of a dummy concrete slab property, so a slab property which has unit moment of resistance in each direction. And then finally, I'm going to assign a pressure load. So I'm just going to assign a unit pressure load, and I'm now in a position to actually do an analysis. So you can see in a few seconds I'm able to define the geometry and apply boundary and material properties and pressure load. If I click solve, then I end up with a simple yield line pattern, which I can then animate just to explain visually or visually describe how that slab is going to deform. And what I can also do is very easily ring the changes. So for example, let's suppose that actually there is a possibility of assigning a support along this edge. I can do that very easily. Before I do that though, just point out what we can see in the output pane. I've actually got an adequacy factor here of 1.046. So that means the multiplier on the applied unit load at collapse is 1.046. So I've not assigned any partial factors, so actually that's a relatively low value. So if I'm able to assign a support along this edge, then clearly it's going to strengthen the slab significantly. And if I do that, then you can see that I end up with actually a much more complex slab pattern, slab yield line pattern, and it's certainly useful then to visualize it. So I've got basically a fan around this this internal corner, and I've got effectively a more complex yield line pattern, which uses up or involves most of the slab. And then from the point of view of margin of safety, I can see that I've got a much larger margin of safety now of 3.284. So that's very, very briefly talked you through the setting up and solving of a slab problem. How did I actually do that? Well, if I nip back to the presentation, then I'll explain how it was done. Now, for the last 30 or 40 years, people have been trying to systematically automate the Yieldline method. Probably the earliest record of a worker trying to do this was Chan in the early 70s. And what he proposed was that you'd discretize a slab using rigid finite elements, and you would allow yield lines to form at the edges of those finite elements. So for example, if this is an eighth of a square slab, you could have a yield line pattern in the location shown in red. However, to get better results, you had to tailor the pattern, or sorry, the arrangement of elements in the mesh. So in order to get the mechanism shown on the right, you would actually have to change your arrangement of elements. And various workers tried repeatedly to improve this method, but with relatively little success. The way we came at the problem was to take a method from a completely different field. What we observed was the relatively little known technique of truss layout optimization, which was developed in the 1960s, could be used to identify, for example, fan geometries, which we often see in yield line patterns. How does truss layout optimization work? Well, what we do is we define supports, loads, and a design domain. We discretize that domain with nodes, and we can use lots of nodes, or we can use relatively few nodes, and then we connect those nodes together with potential, in this case, truss bars. And then we use optimization to find the minimum volume truss to carry that load. And if we have very few nodes, we end up with very simple geometries. If we have more nodes, then we can end up with more complex geometries. So the pattern or the arrangement of truss bars at the right hand side is clearly a fan type arrangement. And what we can actually see is that a modified truss optimization, where actually we, instead of applying external loads and using supports, if we look at the self-stress truss optimization formulation, we can see that actually we can end up with full fan type mechanisms or fan type arrangements if we have enough nodes. If we look at the maths of the problem, it's very simple. What we're doing is we're minimizing volume, which is simply the multiplier of the length times the bar force over the yield stress for all the elements in the problem. And then we have constraints, which are nodal equilibrium constraints. So what we're doing is every node, we are verifying that we have equilibrium in the x direction and the y direction. If it's a self-stress problem, then the external force F here is actually 0. And so I'm showing that again, but this time with the right-hand side of the equilibrium form as 0. And now I've also added a self-stress constraint. And the key thing that we realized is that this is actually analogous to the SLAB problem. The SLAB problem, the maths is exactly the same, the parameters involved are different. So instead of minimizing volume, we're minimizing energy, and the energy is simply the multiple of the length times moment capacity times rotation at yield lines. Instead of nodal equilibrium, we are dealing with nodal compatibility, and instead of imposed self-stress, we have a unit displacement constraint, which will be well known to those of you who are familiar with applying the principle of virtual work in structural mechanics problems. And both boil down to simple linear optimization problems. Just zoom in on the nodal compatibility constraints. What we're actually saying is that if we have a node and we have, say, 1, 2, 3, 4, 5 yield lines coalescing towards that node, then what we need to ensure is that if we traverse around the node, that the rotations in the x direction must resolve to 0, and similarly the rotations in the y sense must also sum to 0, which is completely analogous to applying equilibrium in the truss problem. And finally, a key observation is that although compatibility is explicitly enforced at nodes, it's implicitly enforced at crossover points. So we can have potential yield lines overlapping or intersecting, and compatibility is implicitly enforced at those locations. Okay, so when we'd developed the method over in the university, first thing we wanted to do was check to see that the method was providing demonstrably correct results. One of the first things that we did was apply it to the well-known fixed square slab problem. We can now see here an eighth of a fixed square slab, and there's a known exact solution for that problem. The load factor is 42.851, and that was derived in the early 70s. With the method that we use called discontinuity optimization, DLO, we came up with very, very close approximation of that that number, so 42.857, which is just 0.01% higher. And that work was published in Proceedings Royal Society paper last year. And what we can also see is that if we increase the number of nodes in the numerical discretization, we gradually converge towards the exact solution. So this is a power law extrapolation, and we found actually the exact solution appeared naturally when we did that extrapolation. We also obviously applied the software to lots of literature solutions. Here's just one example. This is an indented slab problem with differing support types, simple and fixed supports. Best solution in the literature was 29.2. We came across a better solution, a lower solution, albeit a more complex pattern. And also in the paper that I've just described, we looked at ways of simplifying the pattern, and this is a technique that we may at some stage include in the LimitState SLAB software. So we can see that it's possible to simplify the solution and to just get a small penalty in terms of accuracy. And then moving on to something a little bit more practical, the work done by the Concrete Centre a decade or so ago involved analysing the slab in the London building you can see in this photograph. You can see on the next slide various different yield line patterns that they tried, and they tried lots of different yield line patterns, and they analysed each of those by hand. And you can see, you can imagine that's quite a time-consuming process, whereas with the LimitState SLAB software, very, very simple matter of getting in the geometry, clicking solve, and automatically you will get the critical yield line pattern, which is relatively complex, as you can see in the slide in front of you. Okay, so I'm now going to hand over to Tom again, and he's going to talk you through applying the software to a variety of different case study examples.
Thank you, Matthew. So as Matthew said, what I'm going to do is just go through a number of case study examples. Firstly, I'll introduce you to the software interface, just to show you the different parts of it, and then go on to the different ways in which you can actually set up and solve a problem. So there's a few different methods, one of which Matthew alluded to, which is the wizards. Also, you can draw things by hand, so that's what I'm going to go through. So do some wizards and arbitrary slab geometry, and then something that's slightly more complex. So if we go back to the software, what we can do is, I'm just going to start something from scratch here. In the user interface, we can see on the left hand side here is where we're keeping all our slab definitions. So that's the slab properties that you might want to apply to your problem. You can create your own, or you can use one of the few that are built into the software. On the right hand side, and perhaps the most important part of the interface, is the property editor. So if you click on any part of the problem, so be it a boundary, a solid, one of the slab definitions in the Slab Definition Explorer, you can see in the right hand side on the property editor here that all the properties of that particular object are displayed. So it allows you to change it. So if I've chosen a boundary, you can change the support type or the spacing of the nodes along it. If you choose a solid, you can change the type of material that's applied to it. also things like the loading and stuff like that. At the bottom we've got the geometry editor, which just allows you to fine-tune different parts of the problem, and then the output window, which Matthew was showing earlier, which will tell you exactly what the adequacy factor is for your particular problem. So if we get on and just go through a simple problem, we're just going to use the wizard to define our slab and then make some alterations to it. So just click on here. We don't want to save the current file, and as you can see, the new project dialog pops up, and all we're going to do is choose a rectangular slab. And this and the other wizard, which is a rectangular slab with a hole, are just designed to allow you to very quickly define an entire problem that can be solved at the end of it. The intention is that once you've done that, you can then make modifications to it to make it more like the slab problem that you may be looking at. So for the project dialog, nothing that you actually need to fill in here, but it just contains a number of useful things like the project name, reference number, and some comments. Also, you can tag files to allow you to then come back, and if you are using Windows 7 or above, you can search through the tags on files to be able to find them at a later date, so you don't have to worry about massively long file names with lots of different complications in them. You can just use the tags there. The next tab on here is setting up the geometry, and we can see that we've got a number of sort of suggested dimensions already, so a width, a height, and also a skew angle that you can add in for your slab. So it doesn't actually necessarily have to be rectangular, it can be trapezoidal as well. We're just going to keep the width and the height and the skew as they are, and then we should change the support types around the edges of it. So in our case, we're going to go from a fixed. I'm going to actually choose simple supports all the way around. So we're going to have a 5 meter by 4 meter slab with simple supports all the way around it. The next tab is the slab definition tab. That allows us to either use one of these existing slab properties that we have in the software, or to create your own. So what I'm going to do is just create a new one, and I'm going to call it slab 1 and give it a color that will differentiate it from those that are in the left hand side there. So I'm going to make it a sort of medium blue color like that. What we might want to do is change the material properties. I'm going to keep it as actually an isotropic slab in this first instance. So you can see here on the right hand side of the dialog, we've got first direction and second direction, and they include moments in hogging and sagging, and also an angle beta. And it's important to, I guess, note that in the software, the angle is the angle at which the MP acts. So it's not the angle of the bars themselves, it's the angle at which the moment capacity is acting. So say we had horizontal bars, then the MP would be acting vertically, so the beta value would be 90. So that's what we've got in the second direction here. So for my slab definition, as I said, I'm going to have it isotropic and keep everything at unit for the moment. You can also input a thickness and a unit weight, so if you were taking into consideration the self-weight of the slab in your analysis, then this would be used to define that for you. But again, we're just going to keep it as unit values for the moment. So the next tab is to define load cases, and in the context of this software, a load case is a combination of some sort of loading along with a partial safety factor set. So you can see here at the top we can choose unity as our partial safety factor set, but we can also create new ones. And if I click on the details button, you can see for this particular case here, unity, as you may expect, everything is 1. So it's also maybe worth noting that the things are sort of couched in terms of sort of the way in which Eurocodes look at things. So you've got permanent, accidental, and variable loading. Obviously, you can use that in whichever way you see fit. If I wanted to create a new one, again, you can put your own user-defined naming, and then you've got the permanent, variable, and accidental. And you can also, if you wish, vary the favourable and unfavourable actions, so ones that increase the load carrying capacity and ones that decrease it. So if I tick that button there, you can see here that it just expands that partial factor set. So you can put in whatever values you like for it. For this particular case, I'm just going to keep the partial safety factors at unity and then look at the type of loading that we're going to do. So we can see here the loading is split into four things. We've got self-weight loads, which by default aren't applied in the software, and then pressure loads, line loads, and point loads. And in this case, because we're setting up through the wizard, it's automatically decided that we want to apply a unit pressure load to, in this case, the only solid which is present in the model, which is S1. You can, if you want to go through, change that and click on the solid that you want to actually select and apply the loading to. So if I can click off it, you can see it disappears there. Click back on it, and if there was more than one, just hold down Control. You can select as many as you want. So we've got a unit pressure which is acting unfavorably, and the important thing here is that the adequacy is set to true. So that's basically saying that the software is then going to multiply up this load when it's looking for a solution until the point of collapse. I'm not going to apply line loads or point loads for the time being. What we'll do is look at those in a different example in a minute. So we've got our geometry, we've got our slab definitions, we've got our loading. All we need now is to set the analysis options, and as you will have seen in Matthew's presentation earlier, we have the sort of concept of a nodal density. So it's how many nodes you are putting in the problem determines sort of how accurately it will model it, and for most cases a medium nodal density, which is 500 nodes in the problem, will suffice. That will get you a solution within a couple of % of the sort of optimum. You can change that to be coarse, so run a very quick problem, which is good for scoping problems out, or you can change it to very fine if you want to be sort of super accurate for any particular reason, but that will obviously take a little longer to solve. Again, what we're going to do, we'll just keep it on medium and finish. So we can see here, if I display the loading, that we've got our problem set up. So we've got rectangular slab, simple supports all the way around it, loading, and that's all we need. So I can click solve. And what you see is quite a standard sort of envelope type failure mechanism. And around it we've got red yield lines around the edges, which are the sagging, and then blue in the middle, which is the hugging. And we can animate that solution. Actually, my PC is a little quick, so it might have gone past a little quick for you. You can animate the solution and just see sort of the way in which that is failing. So it's quite a useful tool to get a deeper understanding of how the problem is actually sort of failing like that. So go back to the top view and unlock it. So we solved it. We can see at the bottom here that we've got solution of 1.22. One of the things we might want to do is then sort of look at changing different things, see the effects that that has. So the first thing we might want to change is to make it from an isotropic slab to an orthotropic slab. So if I click on my slab 1 definition here on the left hand side, you can see in the right hand side, and I'll expand it a little, the slab definition is chosen in the property editor and all the properties are provided there. So maybe what we want to do is change the properties of the moment capacity in one of the directions to be 5 rather than 1. So we're making it, like I say, an orthotropic slab. Done that. If we click solve, again the software goes through and very quickly comes up with a solution, and we can see here compared to before, it's still again the traditional sort of envelope type failure mechanism that you might be used to from hand calculations, but the sort of horizontal portion of it, because of the change in slab properties, has actually widened a bit, and more importantly the adequacy factor associated with this problem is now 3.77, whereas before it was 1.22, so it's gone up by sort of a factor of 3. And also One of the things that may be interesting if you're presenting your findings to a client or something like that is also you can get a report from any of your analyses by just clicking the analysis report menu. You can see down here there are different sections you can choose to actually include in the report. If I click OK, you can see it comes up. All the important things are at the top, so you've got about the report, so just a link to the technology used in the software, and then a summary of everything, including the adequacy factor that's been identified and the critical failure mechanism. And then obviously below that, things relating to the geometry and loading and the slab definitions. And you can save that as a PDF and obviously then present it to whoever you need to. So we've very quickly changed from an isotropic to an orthotropic slab. What I'm going to do is just revert that back to being isotropic, so we're back to the original problem, and we know the related adequacy factor for this is 1.22. What we might want to do is add a column in the middle somewhere, so I just turn the grid on, and then you can start using the drawing functionality on the left hand side here. And to make a column, all we need to do is add a rectangle. So I've got a rectangle, I'm going to add a point, and I'm going to go from 2.2, 1.9 to 2.4, 2.1. So we can see here, column in the middle. All we want to do is select the solid that's in the center of it, the boundaries around the outside, and we just change those from free to fixed. So that represents a column in our problem. If I turn off the grid, we can now just solve it again. If you remember previously we had the envelope type failure mechanism. Now obviously what we've got is sort of a combination of a sort of pseudo envelope around the outside, but then also a fan type mechanism around that column. And we can see that the adequacy factor has gone up from 1.22 to about 2.9, so more than doubled the capacity as we've analysed it there. Next thing we might want to do potentially is to change the edge conditions. So again, just hold down Control, select the boundaries at the right hand side, change that to being free, and solve again. And we can see just by having that free edge on the right hand side there, the critical failure mechanism has changed quite markedly from our sort of envelope and fan combination to being just a failure at the right hand side of that column towards the free edge. And again, we can just animate it to see what's going on there. And the associated adequacy factor is then reduced down again to being 1.5. So that's a very quick sort of overview of how you can set up a problem and quickly modify it using the built-in wizards in the software. There are other things you can do which we don't really have time to go through today, but to add things like point or line loads, and again, like I say, modifying the geometry so you can have different types of slab definition in different areas. So we'll cover that shortly in one of the different examples. So the next thing we're going to do is, instead of starting from a wizard-based geometry, to start from an arbitrary geometry. So as Matthew did earlier, just start with a blank screen with the grid on it. What we can very quickly do is just draw our geometry on the screen using the draw functions that are present in the software. So here I'm just going to draw a cruciform shape. And what we can do is make all the boundaries on that simple. So we've got geometry with support conditions. Then what we want to be doing is adding a material to it. So what I'm going to do is add the unit MP concrete by just dragging and dropping it into that solid area in the middle there. And the next thing we just need to do is add some sort of loading. So these purple buttons up on the top here all define different types of loading. This one on the right is a pressure load, and we get the dialog which was familiar from the first example. So just select all, OK, and we're saying put the unit pressure load on it, on that solid, and put the adequacy on it. So we're going to increase that unit pressure load until we get failure. So we've got all the different things that we need now for our problem to solve. We've got the geometry, we've got the support conditions, we've got the loading. If I click solve, what we get is actually quite an interesting failure mechanism and a solution of 11.73. So the adequacy on the unit point load, pressure load, is 11.73, and we can just animate that and see what happens. What we might want to do in this case is potentially make some of these slides free, add some columns, something like that. And again, we can very simply do that just by clicking on the different edges, making those free. So we've got free edges on there now, and then just adding column supports as we did in the previous example. So in this case, maybe we want 4 columns on these internal corners. So just using the rectangle tool, selecting all 4. So now we've got the cutouts, and all we need to do then is select all those boundaries, set them to fix. So it's quite a different problem already, and it's only taken maybe 10-15 seconds to get to that. So if we solve this problem, what we see now is quite a different failure mechanism. So we've basically got 4 different sections of slab, each with just a line failure through the middle of it. And if we animate that, we turn off the grid, you can see there just what that type of failure mechanism is. Maybe we want to make the slabs bigger. So what can we do there? Again, put the grid on, and it's just a simple case of selecting all of those lines down there and just dragging them across to the new position. We can do that also for the horizontal section of the slab. So make it a slightly fatter problem to be looking at. I'll click solve. And we can see here now we've got quite a nice sort of fan shape coming away from each of the columns in the corners there. And again, I'll just animate it to get a better idea of how this critical failure mechanism is working. It's quite sort of nice flower petal shape that we've got there. So that's, again, a very quick way of getting your problem in there is to just draw it by hand. If it's a particularly sort of simple type of problem that you're looking at that isn't maybe covered by the wizards, then it is quite a simple process, as we've just seen, of drawing something and adding all the relevant parts in order to get a solution. The next thing we're going to look at is actually importing a geometry from a DXF file. So in a lot of cases you may be looking at maybe building slabs or bridge slabs where the geometries are not particularly simple, but you already have CAD representations of them. And what we can do in this sort of case is just import a geometry, and what I will do, if you bear with me, is I will go and find my DXF file. And you can see here I've got a DXF that's called apartment block floor. I can open that, and the DXF import dialog will recognize the different layers on it, and you can say, right, okay, I want to import everything on all of my layers, and the selection at the top says import them as solid geometry objects. So basically what the software is doing is looking for closed loops in those DXF files and saying, right, each of those is a solid in my problem, please make it into one. So if I click OK, what you'll see here is that we've now got a problem that we've read in from DXF that has been changed so that all of the loops in that file have been changed into solids. And that allows us to very quickly get going with the LimitState SLAB software. So we have this problem. All we want to do then is go through and grab the bits which represent the columns and just remove them. So in the same sort of process as we've done previously, we want to be taking out the centers of those and just applying a fixed boundary condition. Oh, I don't want that. So hold down Control and do that, press delete. Actually, you see I accidentally selected a boundary on the right hand side which you didn't want to delete, so you can do that. So it won't be very long. You just delete those, and then you can see we can then select any of these and apply a fixed boundary to it. So now that's got fixed boundaries on it, and we can go through the entire problem and just do that. So we're applying support conditions. In this particular case, our problem has no external boundary supports because these edges are actually cantilevers. All the support is provided by these columns, and so we've got that in there. What we then want to do is go through and apply our slab definitions and also our loading. So for a new slab definition, all I need to do is right click within the slab definition section here, and you can see maybe we want to something called kitchen, and give it a color, make it yellow just so as we can see it, and we can apply our MP values and our thickness and unit weight here. Click OK, and that becomes available within the slab definition explorer, and all we need to do then is just drag and drop onto the relevant part of our model. So we can go through and quickly build up our problem in that way. So with import from DXF, apply the boundary conditions and the slab definitions. Again, we want to apply some loading to it as we did in the manner we saw previously, and you can come up with a model within a few minutes. So what I'm going to do is actually just, in the best of fashions of children's television, here's one that I've prepared earlier, so we can see that we've got the same geometry, but now with all of our slab definitions. And if I click on the loading button, you can see that we've got loading applied in all the different areas that we want to. So now if I just click solve, the software is going through all the different failure mechanisms and highlighting the critical one in the manner we've seen previously. And again, we'll just animate it just to see how that particular failure mechanism moves. So that's the three different ways in which you can potentially import or create a geometry and a problem within LimitState SLAB. So we've got the wizards, we've got drawing things by hand, and we've also got introducing things from a DXF file and then applying material properties and loading, etc. as necessary, all of which will help you develop a model quite quickly. So that's it for this part of the presentation. What I'll do now is pass you back over to Matthew, and we'll take some questions.
Thanks, Tom. So if you have any questions, please just use the functionality in the software. So I'm just looking down the list now. Okay, so just see one question so far. If the slab thickness is different in different areas, how does the software work? Okay, so what you can do in the software is very easily define different regions, and different regions can have different properties. So we can actually see that this example that Tom was looking at earlier, in the main floor, it's got idealized properties in this particular case, but it's got main floor has got an MP in all direction of 1, whereas in the soil area it's also got 1, but we can easily change that. So we could say actually maybe in this area it's got 2, and clearly maybe the thickness is something less idealized than the numbers there. So it's very easy to do. Okay, I'll just see if we've got any other questions. No other questions at the present time. I think time's pushing on, so I'll hand you back over to Tom, who will just wrap things up.
Thanks, Matthew, and thank you everyone for attending today. We do hope that you found the webinar was actually quite informative, and as mentioned at the start, if the presentations raised any questions that we haven't actually answered here, and we appreciate we haven't had time to answer that many, then please do get in touch via telephone during UK office hours or via info@limitstate.com, and we'll be more than happy to speak to you. LimitState SLAB is available to download or purchase now from our website, which is www.limitstate.com, and for those of you who aren't current users of the software, we'll be in touch over the next couple of days just to get some feedback and find out if you do have any further questions. If you'd like to watch the webinar again, or if you think you might know somebody who would be interested to see it, we'll actually make a recording available later on and email you with a link once it's available online, which will be on our YouTube channel. You may also be interested to know that we're actually currently running a promotion where all the new purchases and upgrades of any LimitState software, including LimitState SLAB, receive a 20% discount. This offer runs until the end of September, and you can get more details about it off the news section of our website. Finally, please do look out for our other webinars that deal with LimitState SLAB and our other software products. We'll be sending out event notifications by email in advance of these, and they're also posted on our website at www.limitstate.com/webinars. Finally, just like to say thank you again all for listening, and I hope that you can join us again for one of our future sessions. Goodbye.